Introduction. The flow of water with sediment content is important for hydraulic engineers involved with water supply and flood control projects. Considered as a two-phase flow, water and sediment motion is described as an energy-coupled process, resulting in erosion and scour, suspension, transport, advection, dispersion, and deposition of sediment. Mechanics of sediment transport is important for the design of hydraulic structures in the following aspects. General scour of an alluvial river. Local scour at a hydraulic structure, such as at bridge piers and abutments. Deposition of sediment in flow zones where the existing sediment concentration exceeds the sediment transport capacity of the stream. General scour of an alluvial river. Local scour at a hydraulic structure, such as at bridge piers and abutments. Deposition of sediment in flow zones where the existing sediment concentration exceeds the sediment transport capacity of the stream. Generally speaking, alluvial riverbeds are likely to experience continuous changes over time. In one case, flowing water erodes, moves, and gradually collects sediment in the river, modifying its bed elevation and slightly changing its boundaries. Changes in bed elevation could be resulted from either natural process, general scour, or human activities which lead to alteration of the riverbed or river geometry. Placement of bridge piers inside the river is one of the most common engineering practices in which the bridge pier is in direct contact with the flowing water. The main issue associated with the interaction of flowing water and the bridge pier is the scouring process which occurs around the bridge piers and is known as local scour. Depending on the intensity of approaching flow for sediment transport, local scour process around bridge piers is classified as either clearwater scour or live bed scour. Clearwater scour occurs when there is no movement of the bed material from the upstream flow, while live bed scour occurs when the scour hole is consistently supplied with sediments by the upstream flow. Due to local scour, the flow pattern around the pile foundation will be changed, which ultimately leads to the creation of horseshoe vortex in front of the pier, the wake vortex behind the pier, and the contraction of streamlines at the side edges of the pile. The horseshoe vortex is created by the flow of water separating at the upstream face of the bridge pier where the initial scour hole has developed. Wake vortices develop behind a bridge pier and disturb the downstream flow pattern. These vortices are the main causes of local scour creation, and they lead to an intensification in the local sediment transport capacity and the expansion of local scour around the pile foundation or currents in marine environment. Due to local scour, the insertion depth of the pile reduces as the scour depth around the pile grows, which is directly associated with the stability of pile foundation. The deeper the depth of local scour around the pile, the more vulnerable pile foundation becomes, which leads to bridge collapse in the most extreme case. Therefore, it is commonly accepted that local scour is one of the main causes of pile foundation failure in marine environments. Brion and Hunt declared that 1,502 bridges failed due to bridge scour in the United States between 1966 and 2005. Wardana and Hatapriano also did their research on 500 cases of bridge structure collapse in the United States between 1989 and 2000 and specified that the most common reason for bridge collapse was scour and floods. Therefore, estimation and identification of variations in bed level in the vicinity of bridge piers are crucial for their safe design. The development of local scour hole around bridge piers is jointly associated with the characteristics of flow pattern near the bed and around the pier. The characteristics of flow pattern around the vertical circular piers are clearly fully three-dimensional, 3D, and complex. The tremendous complexity of three-dimensional flow field around a pier is attributed to separation and generation of multiple vortices. It is even more aggravated because of the dynamic interaction between the flow and the movable bed throughout the development of the scour hole, c. The precise prediction of scour patterns around bridge piers depends on recognition of the flow field and the mechanism of sediment transport in and out of the scour hole. Turbulence and the induced secondary flow field around the bridge element have been studied comprehensively in the last decades, both experimentally, for example, and numerically, for example. Many hydraulic researchers have done experiments to investigate the local scour around bridge piers and developed empirical equations to estimate the maximum scour depth. However, most of them were focused on local scour around singular bridge piers, while multiple pile bridge piers have become more common in recent years in bridge design for geotechnical and economic reasons. These types of pier can significantly reduce construction costs with a higher efficiency, though the nature of the scour development in the vicinity of bridge pier groups is more complex than single bridge pier case. Hanna declared that the maximum scour depth around side-by-side piers is approximately 50% more than that around a single pier if the pier spacing ratio is 0.25. Salim and Jones observed that the scour depth decreases as the spacing between the piles increases. The most extreme cases of local scour around ridge piers occur in cold regions where the surface of flow is covered by ice. The influence of ice cover on a channel involves in complex interactions among the ice cover, fluid flow, and channel geometry. This complex interaction can have a dramatic effect on the sediment transport process. The ice cover presence increases the complexity of hydraulic processes in rivers and sometimes extremely influences river characteristics such as hydrodynamics and morphology. When ice flows move discretely and freely, for example, in the case of low surface concentrations of ice pans during freeze-up, the ice resistance effect is slight, and water levels do not modify greatly. In practice, ice cover appears quite often in rivers in the cold regions during the winter. The presence of an ice cover increases the wetted perimeter by adding an additional boundary to the water surface. Under ice-covered flow conditions, the flow is highly sensitive to the friction parameter. The existing number of research on local scour around bridge pier under ice-covered rivers is very limited, due to the difficulties in obtaining field data from ice-covered rivers. Ackerman et al. Did a laboratory investigation on the effect of ice cover on local scour around circular bridge piers. The results showed that for equivalent averaged flow velocities, the existence of an ice cover could increase the local scour depth by 25 to 35% from the free surface condition. Bikuta and Dargahi carried out laboratory tests in a flume with a simulated ice cover for clear water conditions. They found that the extent of scour is larger for ice-covered flows. Wu et al. Studied the effect of relative bed coarseness, flow shallowness, and pier food number on local scour around a bridge pier and reported that the scour depth under covered conditions is larger than that under open channel flow conditions. Objectives. The first objective of this study is to investigate the impact of bridge spacing on the maximum scour depths around multiple bridge piers under open channel and ice-covered flow conditions. The appearance of an ice cover in river changes the velocity profile. Under ice-covered flow condition, the upper portion of the flow is mainly affected by the ice cover resistance, while the lower portion of flow is primarily influenced by the channel bed resistance. The maximum flow velocity under ice cover is located somewhere between the channel bed and ice cover depending on the ratio of the ice resistance coefficient to the bed resistance coefficient. According to Wang et al., it is expected that as the ice resistance increases, the maximum flow velocity will move closer to the channel bed. In terms of transverse flow distributions and velocities of secondary currents, ice cover can impact flows in an existing thalweg, altering the position of the thalweg and changing the morphology of the stream, which in an extreme case will lead to bank and bed erosion. Due to the difficulty of making velocity measurements under ice-covered conditions, nearly all the studies regarding velocity distribution around bridge piers have been carried out using open channel flow conditions. The number of studies on the flow field around both bridge abutments and bridge pier under ice-covered condition is very limited. Zabolansky et al. Performed a series of flume experiments under smooth and rough ice cover conditions and found that the maximum velocity for rough ice cover was 20% greater than for smooth ice cover. This statement was confirmed by Musty et al., who found that the measured maximum velocity under smooth cover is located roughly at 0.8 y0, while maximum velocity under rough cover is approximately located at 0.6 y0, where y0 represents the approaching flow depth. Illustrates the impact of ice cover around the bridge foundation of the Confederation Bridge located in Prince Edward Island in 2015. The ice cover around bridge piers, the Confederation Bridge, Prince Edward Island, 2015.